Hi everybody, I'm Maddie. Welcome to ScienceSideUp. Today we're going to talk about how we know. How do I know? How do we know what the center of the Earth actually looks like, what the interior structure of the Earth actually looks like? So I hope you're ready to take a journey to the center of the Earth. So I bet most or probably all of you have seen a picture like this one at some point in your life. It's probably been in a textbook, right? Where it shows you that the Earth has the crust where we live, and then it has the mantle, the solid mantle, and then under the mantle is the liquid outer core, and then inside that is the solid inner core. But we have never, even to this day, we have never dug through the Earth and looked at it and seen it. So how do we know? That's the question. How do we know what this looks like? So the boundary between the crust and the mantle, which we call the moho, was actually discovered in 1909 by a Croatian seismologist whose name I'm about to butcher, but is written there. And that is Andrej Mohovic. After the moho was discovered, seismologists kept working on the interior of the Earth kind of question. That went on through 1936 when a Danish seismologist discovered the solid inner core. And her name is Inge Lehmann, I think. But again, written there because I apparently struggle with pronouncing Danish and Croatian names. It got humid, so my hair is in a braid now. But okay, so now let's talk about earthquakes. This misshapen ball here, this is the Earth, and that pink X, that is going to be the epicenter of an earthquake. And when an earthquake happens, it sends out two types of waves that move through the Earth. It sends out P waves. P, unimaginatively, stands for both primary and pressure. And then it also sends out S waves. S, also unimaginatively, stands for secondary and shear. Let's talk about what a P wave is. And to do that, I have this slinky. So when an earthquake happens, P waves are sent out first. That's why they're called primary waves. And then the way they work is if this is the Earth, the energy of the earthquake compresses the Earth and then it expands back out. So the P wave kind of moves through the planet like an inchworm. Or another way of saying that is that the direction of propagation of the wave is the same as the direction that the media is displaced. So by media, I just mean whatever it is the wave is moving through. So we're moving this way and compressing stuff into that same direction. I think it's a little easier to see it if we do this vertically. So vertically, a P wave looks like that. And then a secondary wave is different. A secondary wave goes like this, all right? And then it would move like this. So the direction of propagation, right? We're still moving left to right here. The direction of propagation is different than the direction the media is displaced. Vertically, that's going to look like this, right? And then it would go down. And the important difference between those two is that a P wave cannot travel through a liquid, but an S wave can. So P waves can't travel through liquids, S waves can. All right, now let's go back to our misshapen blob that is the Earth. So if the Earth was solid all the way through, here I need orange, then a P wave generated here would come straight down. Apparently orange doesn't work, but that's not what we actually see. We see a shadow. So there's something along this side of the Earth where we see no P waves. We do see S waves, but we don't see P waves. And so the only way that could happen would be if something was in the way. And specifically that if something was in the way that was a liquid. So, sorry, I'm looking for my yellow marker. Because we used yellow to show the outer core earlier. So, we can map out the size of the outer core based off the size of the shadow, where there are no P waves. So therefore, we know we have to have a liquid core. But we also know that we have a solid inner core. Figuring out that the inner core is actually a solid is a little bit trickier than the rest of it. I mean, there's a reason that that took almost 30 years after we started figuring out how to use seismic waves to map out the interior of the Earth, before we figured out that the inner core was actually solid. And so let's go through this just really conceptually. So anytime a wave hits a barrier, right? So like when it transitions from the mantle to the outer core, that's a barrier. And anytime we hit a barrier, the wave can change. So sometimes we have something that starts out as an S wave, and it does its S wave thing, comes through the mantle, hits the outer core, sees that it's a liquid. It's like, psh, I'm an S wave. I've got no problems traveling through. So it keeps on trucking. And then it hits the edge of the inner core and decides that it wants to be a P wave now, right? And since the inner core is a solid, it can do that. So we go through the inner core, but then we hit a boundary again, right? And now we're back to a liquid, so we can't be a P wave anymore. And so it has to go back to being an S wave and then can carry on its merry way until it gets to the other side of the Earth where we measure it with a seismometer. So P waves and S waves travel at different speeds. And that's something that's pretty easy to figure out how fast they travel. You can do that in a lab. So if you have an earthquake that happens here, and then we know how long it takes before we get a signal on the other side of the Earth. If it was an S wave all the way through, it would arrive there at a different time than if it temporarily became a P wave. And so by knowing the speed at which P waves and S waves travel through the different media, and by knowing where the epicenter is and how long it took from the time of the earthquake until the signal showed up over here, we can, through cleverness and trickery, figure out that it had to be a P wave for a little while. So it had to go through something solid. And so that's how we know that we have a solid inner core, just because of timings. And that's maybe an oversimplified explanation, but like I said, it takes quite a bit of cleverness and trickery to figure all of that out. But that's how we did it. That's how we know what the interior of the Earth looks like, what it's made of, even though we have never dug a hole through the Earth's crust. We've never made it out of the green here. I just about knocked my whiteboard over. Yeah, that's how we know. And I think that that question of how do we know that is a really important one to ask ourselves. If science can't stand up to the question of, well, how did you figure that out? Then that's not a very good scientist. So I hope you liked today's video. Please like and subscribe, leave me a comment, and I will see you guys next time. All right, bye.